This video discusses the concept of abstract classes and methods in Java, which is analogous to the concept of virtual classes and methods in C++. I'll demonstrate the same example in both languages, but for this opening segment I'll focus on the terminology used in Java in order to clarify what abstract classes and methods are. Abstract is one of several Java keywords. If it appears in a method definition, then you do not provide a definition for the method. Only the method signature, consisting of a return type and a list of parameters. Because the definition is not provided, it must be specified in a class that extends the class with the abstract method. In this way, an abstract method is like a method in an interface. Because the base class has an abstract method, the abstract keyword must also appear in its definition. Now, in order for an abstract class to be sensible to use, it should contain both a mixture of abstract and non-abstract methods. If a class were to only contain abstract methods, then it would be better to define it as an interface. Strictly speaking, it is permissible to have an abstract class that contains no abstract methods. This simply means that that particular abstract class cannot be instantiated. Instead, some other class must extend the abstract class, and then that child class can be instantiated. However, if there are no abstract methods in the abstract class, then there's nothing to prevent a child class from being empty and not actually modifying the base class at all. The benefit of abstract methods is that you know how they are to be used, and the definition must be provided in child classes. Additionally, you get to blend your abstract methods with non-abstract methods, which means you get to reuse code that would otherwise have to be repeated in multiple classes. Let's go ahead and move on to a specific concrete example in Java. This example will define 3 classes, all of which use this limited access structure abstract class as their base class. These classes are all defined inside of a Java file named abstract.java, which is why the individual classes are defined as being static. But if you were defining these classes in their own separate files, you would omit the static keyword. So what is a limited access structure? So first note that in addition to demonstrating the use of the abstract keyword, this example will also show the use of Java's generic templates. So this is a type variable t, and so what is being denoted here with the definition limited access structure t is that my data structure will contain variables of some particular type which has not yet been specified. Now within the data structure is a protected linked list of elements of type t, and the constructor for this abstract class will construct that list. There is also an isEmpty method, which is defined to simply check if the list is empty. Then we have 2 abstract methods, and so these are the methods that any child which extends our base class must define. We have a put method that puts new elements into the limited access structure, and a take method that removes items from the limited access structure. So all we know is that there is a way to put elements into it and a way to take elements out of it, but we're not sure of what the details are regarding which element is taken out and how elements are put in, etc. But this very general template can be used to define 3 useful data structures. The first of these is a stack. So a stack is a very common data structure in computer science. It is known as a first in, last out data structure because if you insert several items and then remove them one by one, the last thing that you put in will actually be the first thing that comes off, whereas the first thing you put in is buried and comes out at the very end. So this stack data structure, which contains elements of type T, extends the limited access data structure for elements of type T. And because I do not define a constructor here, it is simply assumed that if I construct a stack, then I'll call the default constructor for the limited access structure. This works primarily because this is an empty constructor that takes no parameters, but I could very easily define a constructor for the stack, which then called the super constructor to initialize my base class in a particular way. But all I need to define are the put and take methods. So what does the put method do? It calls list.add. For those unfamiliar with Java's linked list class, this method call adds the new entry at the end of the list. Then the take method removes the element at position list.size -1. So this removes the last element from the list. In other words, put and take both operate at the end of the list, ignoring elements that occur earlier in the list. This is in contrast to a queue. A queue is a first in, first out data structure because if you insert several items and then remove them, the first thing that you inserted will be the first thing that you remove. The queue also specifies a type variable T and also extends limited access structure T. Note that its put method is identical, but its take method is different. We will be taking from index 0. So if we add elements by adding to the end, then that means whatever element is at index 0, meaning the leftmost element in the linked list, was the one that we added first. This is why removing or taking from this structure removes from index 0 of the linked list. Then we have a slightly more complicated data structure, a priority queue. Now, for a priority queue to work, we require that the elements that we insert, which have type T, are also comparable. So we say that our elements T extend comparable, and then there's a question of what are they comparable to? Well, they're comparable to anything which has T as a supertype. Now, usually we're simply going to be comparing elements of one type to the elements of the same type, but this bit of flexibility here allows for more complex contents. Regardless, we extend the limited access structure T. The purpose of a priority queue is to remove a particular element from the structure that has the highest priority, or in this case, the lowest priority value. We will always be removing the minimal element. Now, we're using a linked list for this implementation. Generally, a more efficient implementation of a priority queue would be a heap. And because we're removing the minimal element, this is similar to a min heap. And one could just as easily define the alternative, which is a max heap. But in order to make use of this existing list, we'll stick with our current definition. Notice that the take method will be just as simple as before. All we're going to do is remove index 0. So this implies that we are going to store the elements in our linked list in sorted order so that whatever's at index 0 will always be the minimal element, and whatever's at index 1 will be the next element in terms of order, and index 2 will be the next element in terms of the comparable order. Now, the details of how we do that are in this put method, and these aren't relevant to inheritance, so I'll go through this rather quickly. But what we're doing is using a list iterator, which is a way of going through any type of list structure. I use the list iterator with the linked list because it would be more efficient than repeatedly looking up elements by their index. I have 2 because one is going to be one step in front of the other. And the compare to method is a method possessed by all elements that implement the comparable interface. This basically allows me to check if the new entry that I'm adding is less than the value which came from the list. So once the new entry is less than the value that we just compared to, it means we break out of this loop, because we want to find the position in the list to insert the new entry so that it will remain in sorted order. And it is at that point that we use the second list iterator to add the new element. You can review this code on your own in more detail. I'm going to simply go to our test down here. And so we have 3 bits of code in this main method that initialize a stack, insert some elements, and then have a loop that says while not empty, we print out the elements one by one using take. And this exact same code is repeated for the queue, and it's the same elements that are added in the same order, but we'll notice that they come out in a different order. And similarly, the priority queue adds those elements in the same order, and they will also come out in yet another order. When we run this code, we'll see how these data structures behave. So for the stack, if we're inserting 2, 7, 100, 0, 50, those elements come out in the reverse order, 50, 0, 100, 7, 2. For the queue, they come out in the same order they were added. So since 2 was added first, 2 comes out first. Since 7 was added next, 7 comes out next, then 100, then 0, then 50. Notice these orders are reversed. And the priority queue returns the elements in their sorted order, even though they were added in a shuffled order. 2, then 7, then up to 100, then back down to 0. But they come out in the order 0, 2, 7, 50, 100. We can implement the same data structures using a similar inheritance pattern in C++, though the syntax will be very different. Obviously, the I/O will also be different, and rather than use a linked list, I'm simply going to use C++'s vector for simplicity. Not necessarily the most efficient data structure for this purpose, but it will get the job done. We say that we're using the standard namespace, and in C++, we use templates to handle the generic types. So there's a bit more syntax here, but we're accomplishing the same purpose. We say that our class will be defined using a template with a type name t. It is called a limited access structure, and we indicate that our vector, which is our underlying container, will contain elements of type t, and that the vector is protected. And then we have our public members, so we have a constructor which is empty, because simply by declaring the list, we've implicitly constructed it, so no need to construct it here. And then we have a method that returns a bool. Note that the Boolean type is not included by default. That's why I had to include stdbool in this program. And then rather than say that these methods are abstract, I say they are virtual. And I also have this very curious syntax where I define them equal to 0. Basically, saying that a method is both virtual and setting it equal to 0 is what makes it equivalent, more or less, to Java's version of an abstract method. Setting it equal to 0 requires that the method be overridden in a child class. I could actually leave out the equals 0 portion, and I could even provide a definition for my virtual method. All that would mean is that I have the option of overriding it, but would not have to. So why have the virtual keyword at all? Well, the virtual keyword makes sure that the correct version of the method is called if I have variables of the base class. But for now, we're simply going to treat these as pure virtual methods, which once again are very much like Java's abstract methods, and that's why we define them equal to 0. So as before, we have to define a put and take method, and then we can move on to define our other data structures, starting with the stack. So the stack has to indicate that it uses a template type name t variable, and it extends limited access structure with a type t, and it has a method put and a method take, and the details of this simply depend on understanding how C++'s vector class works, but essentially I am first accessing within my limited access structure the variable list. So this is a scope indicating where that variable came from, and then pushback will put that element at the end of my vector. Popback removes that element from the end, but because this popback method does not actually return the item being removed, I have to first access it using this call to back so that I can return it here. Moving on to the queue, the put method is identical. The take method is slightly different. I access the front element using front, and then I remove that element from the structure using a call to erase and a call to begin. Once again, these are specific details associated with C++'s vector class. Next, I have my priority queue, and the put method here will require me to define an iterator, and I have to indicate that it is an iterator from the vector namespace, but because that vector contains elements of type t, I also have to indicate that I'm using a type name here. So the syntax gets rather complicated, but the code that I'm doing in a moment is actually not too confusing. The name of my iterator is Scout, and by calling the begin method, I'm getting an iterator that is positioned at the front of my vector. I loop as long as that iterator is not equal to the end, so I'm going from the beginning to the end of the list. I get the value being pointed to by the iterator using the star syntax, and then I can simply directly compare the new entry that I'm adding to that value. This assumes that whatever type t is, that it has the less than operator overridden. I'm not strictly requiring it to be a comparable instance as in Java. I'm simply assuming that this operation has been properly overridden. If that's not true, I advance the iterator. Otherwise, I insert the new entry at the location indicated by the Scout iterator. The inplace method will push the following elements within the vector to the right to make space for the new entry. And then the take method is the same as in the standard queue because I'm simply removing from the front. This can all be tested using this main function. I define a new stack, I put elements in it, I print them out. The queue puts the same elements in and prints them out. The priority queue puts those same elements in again. And if I run this code, we'll see that we get the exact same output that we received from the Java code. The stack returns the elements in the reverse order they were added. The queue prints them in the same order they were added, and the priority queue prints them in sorted order. It's worth pointing out that the concept of abstract methods and classes and virtual methods and classes are only really necessary if we have a static type system. If we look at the language Ruby, which does not define static types, we'll see that we can accomplish the same sort of inheritance pattern without any analog to these keywords. I define here a class, which is a limited access data structure. The constructor has a list, which is a new array. An isEmpty method simply checks if the list is empty. Then we start inheriting. So a stack is a type of limited access structure whose put method puts X at the end of the list, and whose take method pops an element from the end. For the queue, I name the class myQueue to avoid a name conflict with Ruby's built-in queue class, but the version of the class I define still extends my limited access structure. I still put elements at the end, but now to take elements off of the front, I use the shift method. Then we have the priority queue, which takes advantage of the built-in binary search capability of Ruby's lists to find where I should insert the element. If the place that I should insert the new element is at the end of the list, then this result will be nil, which is why I have this special case here. Otherwise, I can use the insert method to place X at the right location. And then taking elements is the same as before. I remove them from the front. Now, the focus of this is simply the fact that I can use straightforward inheritance, saying that priority queue is a limited access structure. I didn't have to define put or take up here. I simply access them down here. And if I run code to test this out, you'll see that I'm inserting into the stack, inserting into the queue, inserting into the priority queue. And if I run this code, I'll get the same output I had for the Java and C++ examples. But there is something that you can do in Java and C++ that is a bit different from what I'm doing here. And once again, it deals with the lack of static types. So here in Ruby, although I initialize priQ variable using the priority queue class, I do not declare the type of priQ. Same thing with queue and stack. I do not statically declare their types. This is what makes it easy in Ruby to simply instantiate new classes that have arbitrary methods. But let's go back to our Java example. Here, I have statically declared the types. And in each case, I'm declaring a stack, a queue, and a priority queue. So I'm declaring distinct static types. And strictly speaking, I could accomplish this without using abstract methods. If I were to simply ignore those definitions, I'm removing them, commenting them out, then I can still compile this code and run it and get the same result. The reason is that I'm adding those methods in each of the classes individually, so of course they're accessible if I statically declare each of these variables as being one of those distinct types. However, I am now going to declare each of those static types to be a limited access structure. So even though I will construct a new stack, the type of the variable is limited access structure. Same thing with this queue variable and with this priority queue variable. And this leads to an error. When I try to compile the code, I get various errors. And basically, the issue is that the limited access structure class no longer has a method named put or a method named take. So when I declare the stack to be a limited access structure, even though the stack class defines the put and take methods, I cannot access those methods as long as I am treating this variable like a limited access structure. Same goes for the queue and the priority queue. However, if I go and restore these abstract method specifications, then I no longer have type errors here. Because even though I do not know how take or put will be defined for an arbitrary limited access structure, I know that those methods must somehow be defined in order for this type to have been constructed. Now I can compile this code and I run it and get the same results we were getting before. we'll have similar problems in C++. First, I'll simply comment these out, and because the main function statically defines these types to be stack queue and priority queue, we won't have any trouble. The code compiles fine and gives the same output. But now I'll make the static types of these variables be limited access structures. And attempting to compile here causes problems. It says the limited access structure has no member named take, and similarly, the limited access structure has no member named put. Same problem we had before. This is why we need to have these virtual methods in C++, so that we are aware that any variable whose static type is limited access structure will possess a definition for both the put and the take methods. And once again, we get the same output we've been getting all along. So the presence of abstract and virtual classes and methods can create some headaches for the programmer because it introduces more type errors that can occur when trying to write your program. But as is usually the case with such errors, they force you to think more thoroughly about how your different classes will relate to each other, and ultimately make your code less error-prone by requiring that certain subclasses have methods that actually correspond to what you would have expected any child of a given base class to have.